Okay, so the first big thing is our first test is on Monday. That's the 3rd. And the topics are everything covered in problems up through particle kinematics number 10. So no circular and spherical motion. Or relative motion, which is the new thing we're going to get into today. Relative motion. I guess I will start to, but yeah, to get ready for the test, you're going to just need to go back over the problems as you see fit. You know, like this early in the semester, you may be able to go through all the problems we've assigned so far, maybe if you have like a good bit of time to study. But I'd say overall, like as the semester goes on and these tests are cumulative, so you're sort of trying to be ready for every problem that's been assigned, you know, from the beginning. What I would recommend doing is sort of skimming over the problems, and when you get like at each problem, ask yourself, do I know the steps of how to approach this, you know? And if you know the steps that you would take to solve it, then just think of yourself as pretty good on that one and move on to the next one. And that'll let you sort of hit the ones that where you're a little rusty or a little shaky. Okay. So you should be ready for vectors problems in that math set, and then particle kinematics, except for circular motion and relative motion. Okay. Any questions about the test? Okay, well, today and Friday, if you have any homework questions, problems you want me to go over related to the test, I'd be happy to do that at the start. Anybody have any homework questions right now? So, as far as doing the really big derivatives that come up in those chain rule problems. Chain rule problems and understanding how to go from a path represented as a function to calculating the acceleration as a function of that position parameter. That is important stuff. So I do want to test that. But those problems do end up with really nasty derivatives. And in a 50-minute test, especially, I need to find ways to make these problems reasonably short. Otherwise, like one of those problems could take maybe even more than the whole test, you know what I mean? So for those kind of problems, what I tend to do is I either do the versions of the problem where I give you the velocity as a function of position, and then all you have to do is the chain rule, or I ask for just some individual part of one where you're given the path, you know, so you don't have to, you know, like I might ask you for, I could ask you to give me the velocity vector, you know, given the path and the speed. but then not do the step where you take the derivative, or you know what I mean? So, um, I mean, I'm definitely not going to give you a test that only has one problem on it, you know? So that kind of means those long ones I have to break up and give you pieces of it. Yep.
I noticed that you've been going through REF.
Yeah.
And I just got my calculator.
Okay. No, you won't need it, but yeah, we should just talk about that because it's going to come up in, you know, all my classes. This is of the 3 engineering classes, this is the one that'll come up the least actually. But no, it'll still come up a lot. Yeah. But later on, yeah, but it's really easy. I mean, you know. You just opened the door, Nick. What? That door has been like no one can get in. You must have just pulled it hard enough or something. That's like a paradigm shift. Oh, I guess yeah. um, what? It just works now. Huh. It was like it's like the sword and the stone. It was waiting for someone pure of heart to. I did used to work on electric. Yeah, so you just have a knack for it. Yeah, just felt it right. Okay, any other questions about homework or the test or anything? Yeah, yeah, you can use any kind of calculator on these tests. And not your phone. But and if you know how to take derivatives on your calculator and you're used to doing that, that's fine with me too. I don't want it to be a test of derivatives, you know, but they're necessary. But I would say don't do it unless you've practiced it a bunch because it's just going to screw you up if you're trying to figure it out on the test. But a few of those TI calculators will do derivatives and integrals for you. All right. So the next topic, we just finished talking about circular spherical motion. This is still under the big heading of particle kinematics in non-rotating coordinate systems. So now relative motion, and this is something that you probably saw in Physics 1, probably sort of briefly, but it's going to be a big deal in this class. So we've been doing all these, okay, just imagine. We've been doing all of our calculations dealing with a coordinate system that's not rotating and tracking the motion of objects as seen in that coordinate system. And you can imagine the coordinate system as a video camera, and it's like as the object moves around, this video camera is tracking its location as time goes by. So now imagine 2 separate non-rotating coordinate systems. With the same orientation. And each one is tracking the same object.
When you say tracking, you mean the camera is moving along with the object?
No, it's just keeping track of the location. Each one is, okay, let me change that. Each one is measuring the location. Okay. So here's our first coordinate system. I'm going to call this coordinate system A. And here's our second coordinate system. That's coordinate system B. And the x-axes are pointing in the same direction. You know, they agree on the direction of the x and they agree on the direction of y. We're just going to do that to simplify things a little bit, but it's actually really simple to, if one of those was skewed at some angle, you know, it's a really simple conversion to make it so that but we're going to do it so that the x's agree and the y's agree. And they're both measuring the location of this point. So let's say this is the, you know, the object. And I'll call it the object O. Okay, well, the position vector, the meaning of a position vector is a vector from the origin to the object that you're tracking or the point of interest. And so this is the position vector of O according to this A coordinate system. Okay, and this is the position vector of O according to the B coordinate system. And the notation that we're going to use is this is the position of O relative to A. And this is the position of O relative to B. So it's like a fraction bar in the subscript. Okay. Well, those coordinate systems can track objects, and they also can track the origin of the other coordinate system. So you could imagine, you know, I could draw the vectors like the position of this coordinate system B, talking about the origin relative to A, or vice versa. So so this vector here, move my B, is the position of B relative to A. And the notation before I talk about these relationships. So if I say the position of say A relative to B, that's not just referring to this A and B, but that's just generally what this subscript thing means. We call that the position of A relative to B. And it means the position vector of A that's observed by the coordinate system B. Okay. Well, look at this combination of, so we have these three position vectors. And by the rules of vector addition, you can come up with a relationship between these position vectors. You can see by the directions of the vectors that the position of O relative to A is equal to the position of B relative to A plus the position of O relative to B. Okay, you see that in the vector addition. And so you can see above that this relationship holds. The position of O relative to A, and I'm going to write it in the other order than I just said it, but it's still the same sum of vectors, is equal to the position of O relative to B plus the position of B relative to A. Well, you can think of it as vector addition. It's pretty easy to show yourself if you know what the correct relationship is between these just by drawing out the vectors. But an easy memory device, because you don't always want to have to do that every time you use this, is so memory device is to think of fraction multiplication. So O over A is equal to O over B times B over A. Okay. So if you set up this relative motion equation and you set it up in a way that the subscripts satisfy that fraction multiplication, then you have them in the right order. Okay. Well, if this was only true with positions, I mean, it would still be useful sometimes. But this is the position relative motion equation. So think of that as equation 1 out of 3 of these equations. Well, what do you get if you take the time derivatives of both sides of this equation? So take ddt of both sides of 1, which you have to be able to do if this is true at every instant. And you get the velocity relative motion equation that says the velocity vector of the object relative to coordinate system A is equal to the velocity vector of the object relative to B plus the velocity vector of B relative to A. That's the velocity relative motion equation.
That notation, does that mean object at the end of both sides?
ddt?
No, on the end there's some, of both sides are...
Oh, of equation 1.
Oh.
And then do it again, you know, take the time derivative of both sides of 2. And you get the third one, that's the accelerations. So the acceleration of the object relative to A is equal to the acceleration of the object relative to B plus the acceleration of B relative to A. Third one. And that same memory device works for all 3 of those, position, velocity, and acceleration. If your subscripts work for fraction multiplication, then you have them in the right order. Okay. So one thing that comes in handy sometimes is for any A and B, position of A relative to B is the negative position of B relative to A. This is true for coordinate system origins and objects, and the same is true with velocity and acceleration. In other words, if you write out your equation and it works for the fraction multiplication, but then you're like, oh man, I have the wrong coordinate system expressed in terms of the wrong thing, or I have the view of a coordinate system as seen by the object. That's a little bit of a hard thing to imagine, but it's fine. You just have to use, flip the sign and flip the subscripts. I'll show you, it makes intuitive sense if you look at the picture. Okay, so let's see why that works. What? That's why that's why we're going to do that. Yeah. Yep. Okay, so how does this work? So what if we wanted, so this right vector is the position of B relative to A. What if we got through our equations and we're like, oh, we want position of A relative to B? Well, that's the location of the origin of A as seen in this coordinate system. So that's just a vector from here to there. It's just the exact opposite vector. Just multiply it by -1. Okay. And if you do this in a funky way in one of your terms, but the fraction multiplication works out, and one of your terms says you want the position of A as seen by the object, it sort of makes sense if you imagine the object having another coordinate system on it, but it's a little bit of a funny way to think about it. But just flip the signs, flip the subscripts. Okay. So let's see how this works. So let's say that as an elevator accelerates, a passenger drops their keys. And a camera on the elevator, according to a camera on the elevator, the keys appear to accelerate down at 6.5 meters per second squared. What's the acceleration of the elevator? Okay, so there's the elevator. Here's the sides of the elevator shaft. And what we're imagining is up here, we have a camera in the corner of the elevator that really, to us, what that is a coordinate system. And that's moving with the elevator. Okay. And then fixed to the ground is another, yeah. Yeah, that's what it looks like. Um, um, that thing's supposed to be a key. Uh, and so there's this second coordinate system that I'm going to call G for ground. Okay, it has its axes in the same directions as the coordinate system on the elevator. Okay, and now I'm going to set up the relative motion equation. We're talking about acceleration, so I want the acceleration one. The acceleration of the keys relative to the ground is equal to the acceleration of the keys relative to the elevator plus the acceleration of the elevator relative to the ground. Almost always in these kind of problems, there's the ground, like some kind of fixed coordinate system, and then there's some vehicle or something, some object moving, and then something moving relative to that vehicle. And if you set it up as the term that's by itself is the motion of the object relative to the ground, it works out pretty easily. But otherwise, you can also just set it up in terms of, like, set it up with the left side having the variable you're trying to find, set it up with whatever crazy combinations you need to make the fraction multiplication work, and then just use these to flip the subscripts to make sense out of it. Okay, I'll show you that in a second.
Okay, and that's not this because elevator's on the right.
Yeah, that's not this because, so I did it as acceleration of the object relative to the ground is equal to acceleration of the object relative to the vehicle plus acceleration of the vehicle relative to the ground. And that way of thinking of it always works. Okay, so what do we know? In a coordinate system with the y-axis up, as long as this elevator is near the surface of the Earth, which it is, we know that this acceleration is 0, negative 9.81 meters per second squared. And that's equal to the acceleration of the keys as seen by the elevator, which was given in the problem. That's down at 6.5. So this is 0, negative 6.5. Plus the acceleration of the elevator relative to the ground. This is the one that we want. And now add 0, positive 6.5 to both sides, and you get that 0 is equal to negative 3.41 meters per second squared is equal to the acceleration of the elevator according to the ground. So that's the acceleration of the elevator. That's just the acceleration of gravity in free fall. Like maybe you use 9.8, but you just use that in physics 1 a lot. Yeah, so just out of previous knowledge. Yep. Yes. Thank you. Okay. Well, I always think of it as, like I said, the object relative to the ground is equal to object relative to vehicle plus vehicle relative to ground. But you could also do it like this. Remember that we're trying to find the acceleration of the elevator relative to the ground. And we have three things, an elevator, keys, and the ground. And now we just have to come up with a sum of two vectors that make that fraction multiplication work out. So this is going to be acceleration of elevator relative to the keys plus the acceleration of the keys relative to the ground. And then this one makes sense, the elevator relative to the ground. This one makes sense, the keys relative to the ground. The one that we don't have any expression for is the acceleration of the elevator relative to the keys. And so just use the flip the subscript, flip the sign thing. You get the acceleration of the elevator relative to the ground is equal to negative acceleration of the keys relative to the elevator plus the acceleration of the keys relative to the ground. And now we can fill in the things we know. The acceleration of the keys relative to the elevator is what we were given as 0, negative 6.5. And we're multiplying that by a negative 1. And then the acceleration of the keys relative to ground, that's just free fall. So 0, negative 9.81. And you get the same thing again. Any questions about that? Relative motion and circular motion work together really naturally with rigid bodies. So maybe the most common way to use relative motion is along with circular motion. To represent linkages. Linkages would be a really good name for like a super like overly processed sausage product. But in this context, it means a collection of rigid bodies connected by joints that whose movement have a relationship because of those joints. So let me show you an example. So let's say we have one bar connected to a hinge on the wall. And it has a length of 1 meter. And at this instant, it makes an angle of 45 degrees with the horizontal. And then there's a second bar that also has a length of 1 meter and also makes an angle of 45 degrees. And let's say this first one is moving with a constant angular velocity that way of 10 radians per second. And the second one is moving, has an angular velocity that's constant the other way of 10 radians per second. And I'll call these points, the hinge is A, the connection between the two is B, the end of this is C. Let's say we want to calculate the velocity and acceleration of C. Okay, well, what you have to notice here is according to a coordinate system fixed to the ground, the left body is in circular motion around A. When I say the left, well, actually, let me replace this. So any point on the left body is in circular motion about A. What we are going to care about here is that point B, which is a point on that left body, is in circular motion around A. Okay, so as this thing rotates, this body rotates, the point at the end of it is making a circular path around that point A, okay, according to the ground.
Are these rigid or do they move like an elbow?
They move like an elbow, yeah. So that little dot's supposed to be a pin joint between them. Right. And then this is the key thing that's not as obvious when you first look at it, because that's pretty obvious, right? That point B is, if that bar is moving, that point B is just moving in a circle around A. But according to a coordinate system that moves with B, fixed to B, you know, that coordinate system is moving. The point C is in circular motion around B. Circular motion around, this one should say A, this one should say B. Okay, so we can set this up as the velocity. So the relative motion equation says the velocity of that point C relative to the ground is equal to the velocity of C relative to B plus the velocity of B relative to the ground.
And the coordinate systems are have the origin at those points.
Right. Yep, just, yeah, those 2 points, I guess it is. Okay, so.
And the ground coordinate system would be the front of the wall.
Yeah, it doesn't matter where it is because all we're tracking is velocities, but it's fixed on the wall. You can think of it as fixed at A.
Doesn't matter where you're in.
Not to calculate velocities. You know, a coordinate system that's fixed to the ground here would measure the same velocity for something in the back of the room as a coordinate system fixed to the ground in the back of the room. They measure different positions, but not different velocities. Not velocity vectors, just position vectors. Okay, well, notice that each one of these is a circular motion. Okay, so first let's do the velocity of B relative to the ground. That's omega of the left body crossed with the R vector that goes to B. I'll call this RL. Okay, that's an equation I gave last time in class. What's the angular velocity vector of the left body?
L is the left body, and the left body is
the left body is the upper arm.
So 80.
Yeah. Right. So we know that it's going counterclockwise at 10 radians per second. What's that as an angular velocity vector? Yes. So right-hand rule. X is that way, Y is that way, Z is out. So right-hand rule is this. And so 10 radians per second in the positive Z direction. So 0, 0, 10. And then what's a vector from the center of the circular motion to the point we care about, which is B? Well, let's just describe it, and I'll put in the components. But what? That was given in the problem. Yeah, exactly. So it's just going to be the vector from the point A to the point B. This is the center of the circular motion. Okay, this point is in a circle around A. So yeah, it's going to be 0.7071, negative 0.7071, 0. Cosine and sine of negative 45. And that is 7.071 7.071 0. Yeah, to get the, yeah, just do the power series to get the cosine and sine. 3 terms should be enough. That's an inside joke. But anybody have any question where I got that R vector?
Why are you going from 0.7 to 7?
Because I took the cross product.
Oh, right.
Any other questions? Yeah. So we know that, let me draw. So here's A, here's B. When this thing goes around its circular path, it's going in a circle around A. Okay. The R vector is from the center of the circle to the point we care about. So we're just looking for the vector from here to here. It has a length of 1. If you go from the positive x-axis to there, that's a negative 45 degrees. So it's 1 times cosine and sine of negative 45. When you know y in the cross product gets flipped. So this is the vector RL. And if you look at the picture, you can see that the velocity vector is tangent to the circle, so it has to be like this. And now we're going to think about, now we're going to forget about the fact that B is moving for a second, and we're going to think about calculating the velocity of C around that point B. So the velocity of C relative to B is equal to the angular velocity vector of the right body crossed with another R vector for the right body. So this time we're going, so here's our B, here's our C. The circular motion of C has its center at B. So this is the R vector we want. What's the angular velocity vector of the right body? Yep, 0, 0, negative 10, exactly. So use the right-hand rule. The thumb's pointed in the negative z direction. The magnitude is 10. So we get 0, 0, negative 10 crossed with the components of this R vector are positive 0.7071, positive 0.7071, 0. And we get 7.071 for x, negative 7.071 for y, 0 for z. Yep. Yeah. No, well, cosine for x and sine for y. Yeah. And now we can put this together. We already came up with the relative motion equation we want. So the velocity of C relative to the ground is equal to the velocity of C relative to B plus the velocity of B relative to the ground. And you get a final velocity vector of 14.14200 meters per second. This here was the velocity of C relative to B. And this was the velocity of B relative to the ground. And so what happens is, at that instant, as this body's rotating this way, and this body's rotating this way, that V shape is flattening out, okay? And the effect is that you have a velocity to the right of that point C and no other components, okay? You can see how, I think if you imagine this, you can see how that would come about. Just staying along the line in that direction. Yep. Yes. So if it doesn't say specifically, then we're talking about relative to the ground. Yep, that's right. Any other questions? Okay. Well, bring homework questions related to the test if you have them, and I'll answer that first next time. Yeah.